Thanks a lot for inviting me to your seminar sessions. I'm going to talk about efficient systems programmed using multi-stage programming and also other types of metaprogramming techniques. So I will explain what all these terms mean, right? But first I'll talk a bit about myself. I'm Lionel Parreaux. I actually come from France, but I studied in Switzerland for almost 6 years for my thesis. Which is the main topic of this talk. My thesis was called Types of Metaprogramming and Compilation Techniques for Designing Efficient Systems in High-Level Languages. That's what we're going to talk about now. Currently, I'm an assistant professor at HKUST, which is the Hong Kong University of Science and Technology, since February of this year. And I focus on many other things not shown in this talk, such as type inference and optimizations for compilers and dependent types and stuff like that. Okay. So I will mainly be talking about the Squid framework, which is the framework I developed during my PhD. Squid originally stands for Scala quoted DSL because it was designed in order to easily make compilers for domain-specific languages. And the focus of this framework is type-safe metaprogramming as a generalization of multi-stage programming, which we will explain in a bit, domain-specific optimizations, and extensible DSL compilation. So I will not talk very much about DSL compilation in this talk, but that's another thing Squid is meant for. So the Squid framework is originally an extension of the Scala 2 programming language. It's actually not a plugin for the compiler. It doesn't directly extend the compiler, but rather it's a macro-based library. And in Scala, macros expand at compile time, and that allows you to extend the type system of Scala. So Squid is a set of macros that help you change the way Scala type checks some of the expressions, and it leverages this to encode all the useful features of the framework. And Squid already inspired the development of the Scala 3 macro system because the Scala 2 macro system was very messy. It didn't have nice features. It was quite hard to use. And so they wanted a better metaprogramming framework for their macros and for their runtime metaprogramming. So they took inspiration from Squid in the way they use the type system to make sure that generated programs were well typed, and in the way they allowed pattern matching on code fragments, which are things we will see in a bit. Okay, and this was acknowledged by Martin in 2017 when they were starting to design this Scala 3 system. There's also ongoing efforts to integrate more of Squid's type system features into Scala 3, but they haven't panned out yet. I don't know if they will pan out, but we'll see. So first of all, I would like to talk about the properties of high-level languages, because high-level languages are one of the main focus of my work. I want to use high-level languages because they are easier to reason about. They express what the result should be instead of how to compute the result. This is the usual characterization of high-level languages, right? Most people are probably familiar with it. And so the advantages of this style of programming is that it encapsulates the complexity into reusable modular code. And so it makes programs easier to write and to understand and evolve. And in particular, we're going to talk about Scala, as you guessed, which is a nice high-level language, which was praised in the past for making code easier to understand. And not only easier to understand, but also easier to optimize because it removes a lot of low-level details and you can focus on the important parts that you want to change to make your programs faster. So let's look at a very simple example, okay, almost a trivial example of a program without any abstraction, written in a low-level style, where you try to compute the maximum of 4 numbers. Okay, you can do that by just using a mutable variable result and a bunch of if statements At the end, you return the results. So each if statement updates the results if the result is less than the current considered value. But you can also write these 5 lines of code with a simple, nice expression, a list expression, on which you call the method.max, which is a method in the Scala standard library. Okay, and so this is what I mean with what I mean by high-level code using abstractions. And you can see that this expresses the intent of the code better. It's easier to write, and it's easier to change later. And there are fewer bugs to be introduced in this style of programming because it's more declarative. Okay. One big problem of this style is that it is usually much less efficient than the former style. Okay, so that's why people often resort to low-level imperative programming, because in the end, it's often more efficient. It's not always more efficient. Sometimes compilers are designed to compile specific subsets of high-level languages. And so that's the secret of the performance for high-level languages that are focused on specific domain-specific language. Okay, so there are many examples of this in the industry. For example, you have array programming languages such as Futhark and Halide that have compilers specifically designed to compile high-level programs for a given domain. But these are kind of ad hoc compilers that are designed from scratch, and so it's quite a lot of engineering effort to design. One of the main reasons Squid exists is because we wanted to design this sort of compilers more easily by integrating them in the Scala language itself. So the underlying motivation of all this work is to enable the safe design of efficient systems in high-level languages. So by safe, I mainly mean type safety. By efficient, I mean that it doesn't use so much resources at runtime. It doesn't pay so much for the use of the high-level language primitives. Okay, so why functional programming languages? So Scala is part object-oriented, part functional programming language, and this works very well for domain-specific languages that are embedded in the language. So you don't have to redevelop a compiler from scratch for your small little language, okay? And there are many examples of this using Scala, but also languages like Haskell. I believe you can probably do a lot of this stuff in Kotlin too, which seems pretty appropriate for a domain-specific language. And I guess many of you work on Kotlin. Okay, so what do I mean exactly by metaprogramming? Because I've been using this term, but I didn't really define it properly. So metaprogramming is the practice of writing programs that themselves manipulate programs. That's why it's a meta task, right? So what does it mean to manipulate programs? It may mean to generate programs given a specific input, okay? Also to analyze programs. Given a program, you produce an output. But one particular case of this is to transform programs. So start from a program and end in a different program. Okay, so metaprogramming, I define as mainly these three tasks, okay? And so in the rest, this is what I'm going to talk about in the rest of this talk. First, we will see static typing for metaprogramming, okay, for the tasks I just described. We will see an application of this with a multi-stage programming library for linear algebra. Then we will see how these metaprogramming approaches can combine nicely with compiler techniques to enable more domain-specific optimization of user programs. And we will see an application of that for optimizing a streaming library. Okay, so let's look at this example again of computing the maximum of 4 numbers using either no abstractions or abstractions. So the question is, why is this one slow currently in Scala? Why is it inefficient? And the reason is that a list in Scala is really represented as a bunch of allocations, okay? It's a bunch of cons, cells, allocations this double colon means a list which is made of an element, which is on the left-hand side, and the rest of the list, which is on the right-hand side, and nil represents the empty list. Okay, so in memory, it looks like this. When you have a list of 4 elements, it's a bunch of allocated chunks of memory, which will be needed to be traversed in order to compute the maximum. And obviously, just constructing this thing just to compute the maximum of 4 numbers is kind of silly, right? So let's look at how the list maximum function may be implemented. Okay, this is an example implementation for the maximum function. So we're going to match on the list shape. It can be either something prepended to the empty list or something prepended to a list that is not empty and that starts with the value v. So we don't consider the case where the list is empty, because maximum is only defined for non-empty lists. If there's only one element, the maximum is this element, and if there's more than one element, then we call list max recursively on the rest of the list and compute the maximum between the first 2 elements. Okay, and then we can call this list max function on the list example we had before, and this actually is syntax trigger for constructing this list of cons cells. Okay, what this does is that it computes the maximum between the first 2 numbers and then recursively calls itself until it results in just this simple computation, basically, right? So here I think I'm only showing the maximum of 3 numbers, right? I had 4 numbers before, but that's the same idea. So this is really what the list maximum program is doing. It's just a bunch of calls to the max function. Okay, so the list in this program fragment is not really essential to the computation. It's just overhead and abstractions that you should be able to remove using a smart compiler. These are the computations that we really care about. This int part is the values that we end up consuming and computing, and they are the values that are specified here while constructing the list. So the idea here is to partially evaluate this code in order to produce that code, because it will be more efficient to execute. Okay, so again, this is kind of a silly example. It's made very simple for the presentation. In practice, we have a lot more interesting and complicated abstractions, so that it's not that easy to write the low-level program by hand. So we want this to be done automatically, ideally by the compiler, right? So there's a whole field of study on partial evaluation, and actually for decades they tried to make compilers do partial evaluation by itself automatically, and it never really panned out in a convincing way, because it makes pretty brittle compilers, because partial evaluation doesn't work most of the time, and you don't really know as a user when it will work and when it will not work. And compilers are never really smart enough, okay, to optimize this sort of stuff. No matter which language you consider or which compiler you consider, there are always some limitations that pretty quickly appear, because the search space for optimization is pretty big. Okay, so that's the myth of the sufficiently smart compiler. In principle, compilers should be able to optimize tons of stuff, but in practice they don't. So compilers are not smart enough. So what can we do about this? And this is where my work comes in. So the first idea when you look at this is to perform explicit partial evaluation. So you start from a program and you will modify it so that instead of manipulating integers directly, it will manipulate program representations. In this case, program representations are just strings. Okay, program is a type synonym for string. And so the idea is that instead of computing the result immediately, what we will do is we will generate a program that will compute the result more efficiently. This way, we still maintain the high-level way of defining the results in a way that's modular and that's easier to reason about, but we end up generating programs that are more efficient. So if you look, I replaced int here by program, which is really just a string representing the program. And I replaced the calls to the max function by a string that represents the call to the max function. Okay. So for example, if I call run on a piece of program that is constructed as the concatenation of a lambda expression whose body is a call to this math function, then it's equivalent to calling the output of the. I don't have this expression, but it's equivalent to calling the efficient mathematics expression that we saw before, right? And so this is, of course, limited because string-based program generation is not great. It's very easy to make mistakes. For example, maybe you have too many parentheses, or maybe you have mistakes in the way you compose strings that mean that the output strings are not even well formed. Sometimes you make mistakes because what you generate doesn't have the right type, or it doesn't have the right variables in scopes, etc., etc. And so the alternative to this style of code generation is to use what we call code quasi-quotation, okay? And so this is quasi-quotation because it's like a quotation. It uses quotation marks, in fact, in Scala, but it also uses dollars to escape any sub-part of the program you're generating. And so you can perform any computation in these dollar escapes that return themselves a program fragment that will be inserted in the code quotation or quasi-quotation. We'll use the code prefix here to say that this is not a string of characters. This is really a code representation, and it will have a code type. It won't have a string type. Okay, and this is typed using Scala's type system. So for example, if you write this, when the thing you want to insert inside the quasi-quote is simple, you don't need to use curly braces. So this, for example, is the composition of a code fragment that calls the max function based on these two subcode fragments, and it's typed as code of int. Okay, so it's no longer string based, but now it really manipulates code fragments. And so these code fragments are represented as abstract syntax trees. They're really not strings of characters, right? They look like string literals, but they're actually abstract syntax tree literals. So for example, if I define a val cd0, which is defined as this code quasi-quotation, then in memory, it's really represented as an abstract syntax tree of the plus operation with operands 2 and x here, okay? And if I take this cd0 and insert it inside a bigger code fragment, such as this one, then this really builds a new AST by substituting the right-hand side of this max operation with the cd0 AST value we have previously computed. Okay. Any questions about this? Is this clear? So if there's no question, I'll just move on. Yeah.
Yes, it's clear enough.
Okay. Thanks for the feedback.
Can I ask a question?
Yeah.
I have a question about code type. Why is it code of int, but not code of int, arrow int? Because we have two variables of int type.
I see. So I guess you're talking about this one, right?
Yeah.
So this $u is really inserting an abstract syntax tree in this position, okay? And the type of the code fragment is the type of the quoted part, right? Math.max. Actually, math.max returns a double, but let's assume it returns an integer for the purpose of this talk. So this method returns supposedly an integer, and so the type of the whole code is code of integer. And you insert stuff there that may contain free variables, or that may contain sub-expressions, or even just literal numbers. But the type of this thing is not a function, right? These are not function parameters. These are inserted subtrees. Just the same as we insert a subtree CDE0 here, which is made of this sub-expression, and we get as a result an abstract syntax tree that looks like this.
Okay, so if we just write math.max, then we will have a lambda type, yeah?
Sure, if you partially apply, or if you just write math.max, then it will have a function type, right? Okay, yeah. Mm-hmm. Okay. So quasi-quotes prevent not only syntax errors, but also type errors in the generated code, because we've seen that they are statically typed. And this ties in with the usual the usual statement that well-typed programs should not go wrong. But here we're talking about well-typed multi-stage programs, okay, or well-typed meta programs do not go wrong. So it's an extension of the usual static typing guarantee. And this style of quotation is actually quite old. It appeared in MetaML, which was first formalized a long time ago, right, around 1997. And this was formalized in order to enable the technique called multi-stage programming. So we're gonna finally explain what multi-stage programming is, okay? I mentioned it earlier. So before we explain multi-stage programming, we first need to go back to how programs are compiled, just very briefly. You all know that to compile a program, you take some source code, then you feed it to the compiler, which does some parsing and type checking, resulting in a typed abstract syntax tree. And then the backend of the compiler will turn this abstract syntax tree into some target language. So this will usually be some machine code or some bytecode, Java bytecode, for example, or whatever, or LLVM bitcode. And this is the process of code generation. Now, then when you have compiled your program to the target language, the normal way to use your program is to just run it at some input. You feed it some input, and then it outputs some values. Okay, so that's the normal program execution strategy. Now, multi-stage programs, on the other hand, are a bit different. They are the same in the sense that you still compile programs in the same way, but at runtime, they will actually, when you run the program, you give it some input, and they will actually generate a new abstract syntax tree instead of generating an output directly. Okay, and so the abstract syntax tree, which will be typed when it is generated, will be able to be compiled at runtime into a new target language program that can be executed on some new input, and this stage may itself produce a new abstract syntax tree, etc., etc. So there can be arbitrarily many stages, and at the end of the day, when you have performed all these program generations and phases, you have a final residual program that is supposedly much faster than the original program, on which you can pass the final input, and you get the final output, which is the stream of values you wanted in the first place. And so why is this a good idea? Because at each phase, when we produce an abstract syntax tree and compile it, we can remove some abstraction, right? We can partially evaluate some things based on dynamic values that you pass in the input, okay? For example, these dynamic values could be the sizes of matrices, or even the values of some of the matrix operands you may want to compute or manipulate in your program. And every time you can partially evaluate your whole program based on these partial inputs, right? So multi-stage programming can also be used at compile time, okay? It can be used as part of macros, in which case there will usually only be one stage, because it doesn't make a lot of sense to have multiple stages at compilation time. Multiple stages are really useful when you have runtime values that come at different times, okay? For example, for a query compiler, you may want to first have the queries coming in at runtime to generate some code that will be able to efficiently compile queries based on some new input that will come later, for example, that will contain the specific values that are stored in the table, so that we have more information about which operators to choose based on the selectivity of predicates, and etc., etc. Okay, so sometimes it makes sense to have many stages. Very often there's only one stage. And so if we go back to our example, this is what it looks like. The list max function is redefined. Instead of strings here, we now use code types. So the program takes a list of code fragments and outputs a new code fragment. And now it uses this code quasi-quotation instead of string concatenation to build the final program. Then you can call this compile function, which will perform runtime compilation of a given code fragment that will be composed at runtime. Okay, there are ways of doing this at compile time again, but this particular example uses runtime compilation. Okay, so this will build a lambda expression that is equivalent to this one at runtime, and it will compile it. And after this compile function returns, it gives you a handle to a lambda expression, or a handle to a function value that is just normal Java bytecode for this thing. And it's as efficient as if you had written this directly, right? But this becomes very interesting when you make the whole process work on a lot more abstractions, a lot more complicated programs, and programs that depend on runtime inputs, for example. Yeah, so that's the idea of multi-stage programming. And there are many advantages of this approach. So you can separate static and dynamic data so that it makes it clearer. Also, this phase distinction makes it clearer how the program is meant to work. And this way you delay the evaluation of dynamic computations and partially evaluate the static computations away. And there have been many useful examples of applications of multi-stage programming, mostly on small kernels of computations, because multi-stage programming still is a little limited, as we will see. And so the applications have been rather niche currently, and it hasn't been adopted very widely in the industry. So multi-stage programming is a purely generative technique, by which I mean that it can only generate new code based on some input values, and it cannot, for example, perform analysis of existing code fragments. If you remember, we saw how to compose code fragments together, but we didn't see how to look at existing code values and see what they are made of. So in particular, it cannot perform any program transformation either, right? So it cannot really be used to do optimization, which would start from a given program representation and end in a new program representation. It can just purely generatively generate code and compile it at runtime or at compile time. And this is where Squid comes in, the Squid framework that I have worked on during my PhD. And Squid is a multi-stage programming framework at the root, but it extends this in many directions, okay? It also has code pattern matching and rewriting, so it's not purely generative, it's also analytical. As usual, like most multi-stage programming frameworks, it has runtime compilation, a feature called cross-stage persistence. It ensures the safety of scopes, so that you cannot generate programs that have variables that are defined but that are used but not defined, or that have wrong variable captures. It has different possible intermediate representations. Okay, so I talked about the fact that quasi-quotes really represent abstract syntax trees at runtime, but in fact, it doesn't have to be abstract syntax tree. It could be values in a different intermediate representation, and Squid allows that. And we will not talk about this today, but it also has this notion of stage classes, whose goal is to go beyond the normal multi-stage programming and apply these sort of approaches to bigger software in the large, right? But we will not talk about this today. And if you look at Scala 3 and its new quoted code interface, which is inspired by Squid, actually it lacks a lot of these features. So the main innovation that they took from Squid is code pattern matching and rewriting. They still have runtime compilation, but they don't have anything like cross-stage persistence or pluggable intermediate representations or scope safety. So the Scala style of type-safe metaprogramming is actually not completely type-safe, because it may let you generate programs that are not well scoped at runtime. So let's see what this looks like in practice. If you know the pattern matching syntax of Scala, you write an expression on the left of the match keyword. So this expression is the scrutiny that you scrutinize, okay? And then you write a bunch of case statements with patterns that are supposed to match on the possible shapes of this program. So patterns, again, can be quasi-quotes. So this is a quasi-quote pattern as opposed to a quasi-quote expression. And the dollar escapes inside the quasi-quote pattern represents value that you extract from the abstract syntax tree or from the code representation at runtime, okay? So this will match any piece of code of the shape math.max, where the left-hand side is int.mean value. and it will extract whatever is placed as the right-hand side of this code fragment. Then you have code analysis capabilities using a special analyze keyword, which is actually a macro, and code rewriting, but we will not get into too many details about them right now. Okay, so if we visualize what this does, again, pattern matching on a piece of code that looks like this. Oops, I think I am missing some slides, but okay, let's look at this one, for example. If you visualize the rewriting of a piece of code, given this pattern. So here we're rewriting math.max on the minimum value as the left-hand side to just the right-hand side. So if you take a program that looks like this, for example, and you apply the rewriting, then the rewriting will match specifically this part of the AST. It will go recursively into all the sub-trees of the AST. It will match this math.max method call and this mean value constant, and this right-hand side will be extracted as V, and the whole thing will be rewritten as expected, right? So there are many challenges for statically typing this sort of program manipulation. Remember that what we want to do is that we want to type check meta programs so that at the compilation of the meta program, we ensure that it cannot possibly manipulate programs in the wrong way, in the sense that it cannot generate programs that are ill-typed or that contain unbound variables, okay? Or variables with the wrong type, right? So the first challenge is to keep track of scopes, as I've already mentioned. So for example, if you look at the program, such as this one, and at a rewriting such as that one, here we are matching any map expression which is passed to lambda with some variable and some body, and we are rewriting this to an expression that uses a different variable name as the lambda passed to map, okay? That could be a rewriting that maybe you want to write and you make a mistake, and instead of x here, you just bind y. And this transforms the program into an ill-typed program because the x variable is no longer bound in the new program, or it could be capturing some wrong binding later on, and the y variable is not used. So how do we avoid this? The way Squid avoids this is that it actually adds a new type parameter. It's not only code of type, now it's code of type in some context, okay? And the context is actually a type that represents the context dependencies of the given piece of code. So Squid also has a concept of first-class variables so that you can extract, you can use escapes in variable positions, okay, in variable binding positions. And so here you don't want to match programs with a specific names, right? You want to match any possible variable that will be bound here. And so you write a $x to extract this variable binding. And if you try to rewrite this into that, now you will get a type error. Squid will tell you the rewritten program doesn't have the same scope requirements as the pattern that you are rewriting. Okay, and if you write it correctly, then it type checks and it works correctly. So at compilation of the meta program, it makes sure that the scopes are respected, and it uses this. It does this through quite advanced type system trickery to maintain a reference to the context in the static types of code fragments. So if we look into more detail about how this is done, so the top level code context is any, and it means this piece of code can be used in any context. And the code type is actually contravariant in the context. And so then you can intersect, you can use specific variables for standing for this context, and you can intersect them, which means the requirement of both C and D in this case. So Scala 2 has some form of type intersection, and they are used here thanks to the contravariance of code fragments, in the way that, for example, if you have a code fragment that is usable in any context, you can also use it specifically in the context D, and you can also use it in the context C and D, okay? Okay, and actually, when you have specific variables such as V and W, it uses path-dependent types to track the specific dependencies on the variables V and W. So, for example, if V was extracted from a binding pattern, then the code that uses V will have type code of some type in the context v.context. So this is a path-dependent type. It's a type that's distinct for each V, for each specific value. So v.context and w.context are distinct types, and it makes the intersection of them in order to represent the context dependencies of both variables. Then you have useful helper functions such as .without, which try to remove a variable dependency from the type if the variable ends up not being used in the code fragment. Otherwise, it returns none. So here's an example where we construct a code fragment depending on two variables. And then here's another one where we have a code fragment that depends only on one variable, but whose context is ascribed as depending on both variables. Then if you write this code fragment without w, without the variable w, then you get some of the same thing, but without the context dependency in its type. There's another challenge about analytical statically typed quasi-quotation, which is that you need to be able to extract types from programs, not just variables. Okay, so if you look at a possible fusion that you may want to do on a given list, so if you could map twice on a list, you can rewrite this to a single map call with the composition of the two functions. You may want to write it like this, but you may also want it to work on lists of any types, right? And so the question is, what do we write here? We don't want it to only work on lists of integers, for example. And we don't know the type of the lists that are used in a given program because this type information is not available at the top level of the program. So what we need to do here is to extract types. So we can also use $escapes in type positions using Squid. And this will actually work out in the type system by using the corresponding context dependency types to track that you are doing things correctly. So in this particular case, what this means is that we extract excess, which is a list of any type tie, and then you construct a new map call using this same tie type as the parameter type, and you can compose the two functions in this way. And Squid will actually inline the regex here, the reducible expression. If you take a lambda expression and apply it directly, then Squid will rewrite this into a let binding, basically, a val definition. Okay, another challenge in doing this is that you need to be able to constrain existing types from programs. So what do I mean by this? If you look at the transform function, that should work on any type and any context, so any type T and any context C. So say it wants to take a code fragment of type T in context C and return a code fragment of the same type and the same context. And it wants to match this code fragment on a specific expression form, such as integer addition. Okay, so for example, it wants to rewrite additions with 0 into just the left-hand side of the addition. So this is the way you write the pattern in Squid. But here you can notice that the left-hand side will have type code of int in the context C, but what we expect is a code of T in the context C. So how does this work? Currently, there's a type mismatch if you don't do anything smart, right? These types are not the same because T should be able to be any T, and int is more specific. And so the way this is done is that Squid keeps track of subtyping relationships between the currently considered pattern and the value you are currently matching. So it sees that you are matching a code of type T with a pattern of type int. And from this, it infers the fact that T in this branch is actually a supertype of int. And this means that this rewriting is actually correct. Okay, you can return a code of int, and that's a subtype of code of T because code is covariant in its type parameter. For those familiar with generalized algebraic data types, it's essentially the same problem, right? In Haskell, they have problems like this in the context of generalized algebraic data types. There's finally something we need to talk about, which is hygiene and the way we avoid.
Lionel,
Yeah, go ahead.
you said about various types recurring. Which type features are essential to implement all this fancy stuff? Do we need especially hidden types or path dependent types, or we need DDT to do this, or do we need something else? Could we port which features of type system of a language where we should repeat your work, when we want to repeat your work, are essential to be able for us to repeat your work?
Okay, very good question. I would say there's a bunch of things if you want to support all the features that are shown here. One of the things that definitely is that you want to be able to have a code type that is covariant in the type argument and contravariant in the context, so that you can have this sort of subtyping relationships. You also need to have path-dependent types if you want to be able to reason about individual variables, right? So this v.context is a path-dependent type. So as you say, path-dependent types are something you really need if you want to ensure scope safety completely, right? There are other ways of ensuring some forms of scope safety that are a lot more restricted. So you could get around not having path-dependent types, but it would either be very restrictive or actually unsafe in some cases, which is the case in Scala 3, for example. Besides that, there's some type system adaptations you need to do, especially generalized algebraic data type style reasoning, right? So this is what's going on here. Scala 3 actually added this sort of reasoning in the compiler. So if I were to implement this quotation, this approach in the Scala 3 compiler, it would be a lot easier to implement. Here, I had to re-implement this feature in the Scala in my Scala 2 library. So I would say it's quite an important feature if you want pattern matching on code fragments, right? Because it often happens that the pattern you're matching on doesn't have exactly the same type as the scrutiny. So in this case, you need to be able to reason about local subtyping relationships. And this is quite an advanced typing feature, okay? So these are the main features that you need to have the full generality of Squid statically typed program manipulation. Does that answer your question?
Did I understand right that you need a typed tree where all nodes of this tree are indexed, have indexes with the type which this expression has? So it is required.
So you can have you can have different levels of safety, right? If you want to ensure that well-typed meta programs soundly manipulate programs, meaning that they don't introduce type mismatches or they don't introduce unbound variable errors in the manipulated programs, then you need this. Yeah, you need to index code types on the type of the program they represent. But if you want to avoid that, you could also avoid that, but you would have fewer guarantees, right?
Okay. Okay, thanks.
Sure. Okay, I realize that I need to speed up because so I'm not really going to talk about hygiene too much because it's kind of not very important. Maybe just give an example where no, I'm not even going to talk about the example. So let's go straight to the application example of the polymorphic linear algebra language, okay, which is a paper that we recently published at ECOOP with my colleague, Amir Shaikha. And so the motivation of this work is that many data analytics tasks boil down to linear algebra, as many of you know, okay? So many things from machine learning to computer vision, simulations, etc. But different domains use different representations and types of these linear algebra concepts. Okay, so they instantiate the idea to different concrete types. For example, for graph algorithms, the matrices are typically made of Boolean values. Okay, and so the operations you're doing in graph-based linear algebra are mostly Boolean conjunction and disjunction, and in other applications of linear algebra, you may want actually real numbers if you want probabilistic graph reachability problem solving, for example, okay, using matrices again, but instead of Boolean values, you have now real numbers. And you also have lots of different possible representation types. For example, if you want to compute the derivations of matrices, then you may want to use dual numbers, which are actually a couple of two numbers. And so obviously all these different representations use different computation models and are implemented and optimized differently. So in practice, what happens is that each workload used by actual data scientists use a specialized implementation of these techniques. Okay, so there are many implementations of linear algebra for different specific domains and representations. The reason we don't have a single representation to rule them all is that there would be a big performance overhead due to this abstraction. And so the idea here is to make a completely polymorphic library that can be reused, that works for all linear algebra workloads, but that uses Squid metaprogramming in order to automatically remove all this abstraction. Okay, so this is going to use the abstraction capabilities, the metaprogramming capabilities that I have just presented. So the framework we defined is called pilatus. It stands for polymorphic iterative linear algebra that uses staging. Okay, it's actually the name of a mountain in Switzerland, and it's implemented as a few hundred lines of code, relying on Squid for all the complicated metaprogramming primitives. And it allows you to define linear algebra programs that can be specialized to different representations that end up being as fast as handwritten low-level code. Okay. So pilatus merges ideas from different domains, the domain of abstract algebra in programming languages. So it reuses the notions of semi-rings and rings and modules from mathematics, but also uses programming language concepts such as final tagless, pool arrays, and multi-stage programming. So what do we mean by that? The tagless final encoding, which is also known as object algebras or polymorphic embedding, is a way of defining sub-languages or domain-specific languages using interfaces that are parameterized with some types. So, for example, here we represent the concept of a semi-ring with any representation R, okay? So this is an interface that works for any given R, and that defines how this R is supposed to be treated as a semi-ring. So it means that this R must have an addition operation, a multiplication operation, a 0 element, and a 1 element. And then you can actually, you can use this representation using implicit parameters, which is the way Scala implements type classes. Okay, so this can be used as a type class for those who are familiar with this idea. And then you can write programs that are fully generic on the particular implementation of semi-rings, and that can use multiplication, addition, and all these features provided in the semi-ring interface. So that's the basic idea of object algebras or tagless final, and we use it throughout the framework for anything that's related to linear algebra, not just semi-rings, but also matrices and stuff like that. So, right, and you also implement this interface for different actual types, right? So, for example, you define the semi-ring of Booleans as an object called semi-ring Boolean that defines the operations add, multiply, 1 and 0 using the Boolean interpretation of these things. Okay. So this is nice because it's very expressive. It's a nice little DSL that's embedded in Scala that can reuse the type system of Scala to implement all sorts of algorithms with different representations. But there's a big problem with this approach, which is that well, the performance is actually 10 times to 100 times worse than handwritten code. And this is because this approach involves a lot of abstraction and a lot of modular design that is not good for the compiler, for the runtime performance of the program. And this is where our approach comes, where the Squid multi-stage programming approach comes in. Okay, and the main idea of our paper is that you can implement the smearing interface for code fragments, right? So it's the same multi-stage programming approach, but applied in this specific case for type classes and for tagless final. So if you want to, you can define a smearing code class, which will create a smearing instance where the representations themselves are not concrete number representations, but actually code representations, okay? And the way you add two code representations is by creating a new code representation, which will insert the smearing implementation of the underlying type and generate a method call to this underlying type, okay? And then you can use the Squid framework to perform partial evaluation, algebraic simplification using pattern matching and fusion of the created arrays, etc., using the same approach of multi-stage programming that I've explained in the previous part of this talk. And this, in practice, it looks like this for very simple algebraic rewritings. Here we override the add definition in a given implementation, and we match on the operands of the implementation so that if the zero method is used on either side of the operand, then we rewrite the subprogram accordingly. And this polymorphism helps us to generate, to optimize programs in the end, because this means we have gone from programs that use linear algebra computations, and we have made them into programs that actually generate programs seamlessly thanks to the tagless final interface, right? And this means we can optimize these programs very much, and we can reach the performance level of low-level code, actually. Okay. So I think I will stop here because I have many more slides, but I didn't realize that it would take so long, and I'm out of time. So I guess I will just skip straight to the final slides, and I'll take any questions. So thanks for attending. Yep. Any questions about this stuff?
I have one. Thank you for the talk. The first one is pilatus implementation available?
Right. So I think the pilatus implementation is not currently available. You have to see with my colleague Amir Sheikha, who is the lead author of this paper. We have an implementation, and it was evaluated, but we are currently working on re-implementing it in Scala 3 so that it doesn't use Squid, because Squid is only available for Scala 2, unfortunately. But Scala 3 completely changed everything, and so we're kind of moving away from Squid now. Unfortunately, Scala 3 doesn't support all the features, but yeah, for better reusability and for the health of the system, we're rewriting it to Scala 3.
But can we get any more or less stable version for experiments?
Yeah, I guess you can. Yeah, I guess you can contact Amir, and he will be happy to provide you the code. But it's not meant to be a widely used libraries that we want to support, right, and maintain, right? So that's why it's not given as a public repository.
Thank you. The next one is about what do you mean by low-level implementation? Is it C implementation of or something else? So,
in this case, what we usually mean is an implementation in Scala, but that only uses very low-level constructs such as mutable variables and while loops, and typically it will use only primitive types like integers and whatever, and it will avoid allocating things. It will avoid virtual dispatch, stuff like that. Yeah.
And in your work, you use only sequential implementation, so no vectorization, no parallelization.
Yeah. So the JVM sometimes does some automatic vectorization, but so we sometimes benefit from it, but we don't do anything specifically for it, right?
I see.
It doesn't kick in usual stream programs, for example, because there are too many abstractions that the JVM needs to go through. But thanks to staging, we can just generate directly the nice low-level code, and then it can do a lot more with this.
And more about pilatus. Can it operate over sparse matrices, or it can operate over dense matrices?
Pilatus itself is for dense use cases, but we are actually working on applications for sparse linear algebra. Okay, so there's a new language called SDQ.
Cool.
Yeah. And so we definitely want to extend it in that direction. Yeah, but that's not currently done for pilatus.
Thank you.
Yeah. Thanks for the questions.
Cool. I got curious how much low-level Scala implementation is lower than C implementation of the same stuff.
Say it again. I didn't catch.
I believe the low-level Scala implementation should be slower than C implementation.
Okay. So the
how
thing
many
is,
times slower?
The thing is that we only generate very basic primitive types using code, and so I guess that using Scala native, you can actually reach similar performance levels as C. We haven't really experimented with this.
Why Scala native? I believe it is required for better startup of your programs, not for better performance. No.
Well, Scala native will generate LLVM bitcode, right? And so we could theoretically benefit from all the optimizations that a C compiled program would, as long as it doesn't use a lot of abstractions. And that's already what we do, right? For better performance on the JVM, we try to avoid all the virtual function calls, all the memory allocations. And so in the end, what we get is something that looks pretty much like a standard C program, right? Scala native is not as fast as C, because normal Scala code allocates lots of code and has lots of virtual dispatch. But if you feed to Scala native some C-looking code, then I expect it will have similar performance.
Okay.
Make sense?
I will believe.
Yeah, we haven't actually made thorough experiments on this, but there are a few things that we need to be careful with. For example, JVM types don't always map directly to C types, right? We want to use the real C types to have the best performance, and Scala native supports that, but we haven't really investigated it too much.
Well, I basically wanted to know how performant is code written in Scala, because your topic is somehow about performance. Looks like. Also, I have a follow-up question about type trees and previous stuff. You said that you need type at abstract syntax tree annotated with types of every expressions in the nodes. What kind of types it is? If I can easily believe that if expressions have some basic types like ints and functions, it's easily doable. But what about the case when your program defines some user types and then writes expressions and it consists of expressions that should be typed by user-defined type?
Right. I guess that's a very good question. The basic answer is that Squid doesn't have a set of built-in types. Squid actually integrates with the Scala type system so that you can represent any type that is defined in Scala by different users, right? It's not like a closed world assumption. Obviously, the big problem with this is that you may want to perform optimizations on these types, and Squid doesn't really have access to the definitions of the types, and it cannot really change them to compile them to more efficient stuff. And this is what we've been looking at for, do I have an example for this? So I have some work for multi-stage programming in the large with stage classes. And here the idea is that you also stage user type definitions. So you let users write their own classes, but the classes integrate some staging information that Squid can reuse in order to compile better code for these user types, right? So yeah, the short answer is that Squid supports any types users define, but it won't optimize them specifically because it doesn't have access to them. But you can use stage classes to have better optimizations for these types.
But you still have a type at syntax 3 where every node annotates the type.
Yeah, so this actually depends on which.
So if there is some code which is typed by user-defined type, which type annotates this node in your type at abstract syntax 3?
So there are some constructs for arbitrary types, right? For example, in Squid, there's a construction for an applied type, and it's based on a type symbol that denotes any possibly user-defined type, right? So it's represented as a fully generic type system, basically. And it uses the symbols of the Scala compiler to identify user-defined types. I don't know if that's what you're asking, or if you're asking something else.
It sounds rather complicated. Maybe I should try to understand it, not in the questions of this talk. Maybe later.
Yeah. So actually, it's even more complicated than this in a sense, because the thing is that if you remember, the Squid intermediate representation is not fixed. It doesn't have to be a normal type TST. It could be other things. It doesn't have to be typed even. You could use intermediate representations that are not typed, but if they're not typed, then you cannot perform rewriting on them because rewriting needs type information. But the point is that Squid provides an interface for what it means for programs to be typed. So it provides a way of constructing type representations. I can actually show you this, I guess, if you want to make it more concrete. This would be in, what is it called? I think it may be here. Oh, no, it would be in this one. So this is basically a tagless final representation for Squid types. Okay. I don't know if you can see my screen. Can you? Oh, maybe you don't see it. Okay, I need to actually.
I don't.
I need to share it. Oh. Oh, share this tab instead. Okay, got it. So yeah, okay. So this is the Squid repo. There's a lang package which defines the Squid language in terms of finally tagless approach. Okay, so it's a bunch of traits, and it has this final tagless approach for constructing type representations. Okay, so there's this type rep object which is abstract in this representation, and it has different constructors for type reps. It has the type application constructor. It has constant types because Scala has constant types. It has type symbols to construct the representations of given types, etc., etc. And so in practice, you have implementations of this trait for each intermediate representation that you may want to use. For example, if you look at the let's see. Oh, it wouldn't be in the core. It would be in the source. So if you look at the simple AST, this is the actual implementation that defines all the functions required for an intermediate representation to be compatible with Squid. And in particular, it defines the ways of constructing the different type forms. I guess it's defined somewhere else yet. Probably in AST helpers, maybe. Yeah, sorry, I haven't worked on this part of the code base in a while, but I hope you get the idea.
Okay, thanks.
Yeah, no problem.
Maybe somebody else has any questions.
Yeah, I have a small comment on sparse linear algebra again.
Yeah, okay.
Do you know about GraphBlast?
Yeah, I know about it.
Okay. So it looks like it can be a cool evaluation for your ongoing work.
Yeah. Thanks for the
to implement
suggestion.
some algorithms in terms of sparse linear algebra for graphs. Yeah, it's cool.
It's definitely one of our intended use cases, right? Among other things.
And can we implement something like stream fusion, but for example, for matrices using your approach? For example, can we avoid intermediate matrices construction by your approach, by using your approach, or not?
Yeah, so there are several ways of looking at the problem. In a purely multi-stage programming way, I guess you can use exactly the pilatus approach, but change the representations a bit so that it supports sparse linear algebra. But the same approach should work, right? For doing fusion on matrices, you just define an abstract interface for matrix operations on arbitrary types, and then you use staging to generate programs from given linear algebra programs. And since you're generating programs, you have the actual representations that you can change the program on the fly, right? So if you see some operations done on the same matrix, you can merge them together or stuff like that. There's another approach to stream fusion which I didn't have time to go over, which doesn't use multi-stage programming per se. Instead, it looks at normal Scala programs and optimizes them through rewriting. So that's another way you may want to look at things. It has advantages and drawbacks. The main advantage is that it's less intrusive, because when you use staging, you basically require users to go through your interface, and you cannot really write your own code. Or you can, but if you want to write arbitrary code, the user may actually need to write quasi quotations, like staging annotations themselves. So it's not great, and so there are other ways of doing things. So this other approach simply relies on pattern matching and rewriting to do this.
I see. Thank you. So yes, it should be possible. Okay.
Yeah. I see there's a question from Brendan. There's a Okay.
Thanks, Lionel. This is really great.
Thanks.
I have a question about the developer tools, and in your experience when you're developing these embedded DSLs, how easy is it to make a mistake that isn't checked by the type system? And when you do make a mistake, how do you find the debugging process? So you have to inspect some strings, or is there a way to localize these errors in the editor? Thanks.
So I guess there are several levels to this question. There's a bunch of things that the type system prevents you from doing, such as generating programs with the wrong type or the wrong variables. And for this, we rely on the Scala's type system. And so you're gonna get Scala style type errors, right? You can, so for this, the same approach that you would use to debug Scala type errors applies. It's not always very easy. There's actually some tools provided by Squid that makes it easier, so that you can, for example, instead of code in the quasi quotation, you can write you can write dbg underscore code, and it will print some debug information about how it's processing the code, and so you can see what it's doing and why it inferred that or that type or that context or whatever. So that's for the part of the system where you ensure static types and variable bindings. But there are also many possible errors you may do while writing program transformations and program generation, which are more like logical errors, right? One of the common one is to write a rewriting that doesn't terminate because you make a fixed point, but actually it generates infinite stuff. That's not very nice to to debug, because you just get a Stack Overflow or something and you have to figure out why. And then there's a class of errors that I haven't talked about, but I have slides about it, which are errors related to the effects of the program you're manipulating. It's easy, if you're not careful, to rewrite programs in a way that is unsound with respect to the effects that the program may have. So I have an example here. So if you try to rewrite map fusion, if you try to implement map fusion with a rewriting, you may be tempted to write this and do this on the standard abstract syntax tree representation, but this would be wrong because, for example, you may be passing to map some effectful operations, and then the fusion is no longer valid, at least for lists. It would still work for iterators, for example. And the way we solve this is that we use an intermediate representation that has a notion of effects, and that actually prevents this sort of stuff from happening. But if you're making the mistake of writing this sort of rewritings in the normal AST representation, you will just get wrong rewritings, and debugging this will be pretty painful. I don't know what sort of tools would help. I guess it would be very useful to have a representation of how the rewritings execute and operate on the original program. This is something we were looking at some point. It would be nice to have a graphical representation of the different stages of rewriting as a tool that would be super useful for developing macros and code rewriting.
Yeah, I kind of think the graphical debugger is a helpful thing.
Yeah.
Thanks.
Thank you.
Does anybody else have any questions? Well, I'm personally very glad that we invited you. It was very interesting and understandable talk.
Okay, cool. I'm sorry that I had too many slides, and I thought since it was a long talk, I would have time to talk about everything, but actually not at all. But okay.
It is common issue we talk.
Yeah.
I definitely understand what this problem.
Okay.
Semyon had something to say, no?
I have a small comment. Is it possible to share your presentation to investigate all your slides?
Yeah, I will do that. Sure.
You could share it on the web or send me an email. I will pass it to Semyon.
Where should I share it then?
You mean you could put the slides on the web, GitHub pages, stuff like that? I don't know what is more.
Yeah, I can put it on my website, sure, so that it's easily accessible.
Okay.
Thank you.
Thank you a lot. It was very interesting.
Thanks a lot for the invitation and for all the questions, and it was a pleasure to be here. Okay, and maybe we'll talk again about type inference at some point.
Yeah, I hope it will happen.
Cool. Okay, so see you later.
See ya. Many thanks.
Thank you.
Bye.
Bye.